Deep in the Indian Ocean, gravity is weaker than almost anywhere else on Earth. Here the sea level dips over 100 meters below the global average. Not because water is missing, but because the planet's pull is less. This invisible anomaly is a clue to the restless forces shaping our world. For decades, scientists puzzled over this gravity hole, challenging the idea of Earth as a perfect sphere with uniform gravity. To solve the mystery, we must look deep into the planet's molten heart, where ancient processes still ripple to the surface. The answer reveals not just a single anomaly, but the dynamic, ever-changing nature of our planet. Earth isn't a perfect sphere, it's more like a lumpy potato, with mass unevenly distributed beneath its surface. These lumps and dips create subtle variations in gravity, forming a landscape of invisible hills and valleys called the geoid. Satellites map these gravitational quirks, revealing a planet shaped by shifting continents, rising mountains, and the churning mantle below. We don't feel these changes, but our instruments do. This uneven gravity drives the movement of tectonic plates and the rise of volcanoes. Nowhere is this more dramatic than the Indian Ocean's vast gravitational low, a sign of deep, ongoing geological change. It's a reminder that Earth is alive, its surface just a thin crust over a roiling interior. The Indian Ocean. Geoid Low is the planet's most dramatic gravity dent, stretching over 3 million square kilometers. Here, gravity is at its weakest and the sea surface dips more than 100 meters below average. This isn't just a surface feature, it's caused by a mass deficit deep in the mantle. For such a vast region to have weak gravity, something lighter than usual must lurk far below the crust. The ocean simply follows the shape dictated by this hidden landscape. For years, geophysicists searched for answers, knowing the solution lay deep within the Earth. The breakthrough would come not from drilling, but from simulating millions of years of Earth's history. The mystery was about to be unraveled. In the realm of geophysics, where the Earth's deep secrets lie buried, Indian scientists Debanjan Pal and Atreyi Ghosh embarked on a fascinating quest. They sought to unravel one of the planet's most perplexing mysteries. Their mission: to solve the mystery of the Indian Ocean's gravity hole, a vast area where the Earth's gravitational pull is significantly weaker than average. They set out to accomplish this ambitious goal by simulating a staggering 140 million years of Earth's evolution, a journey through deep time. Their complex models included the dynamic movements of drifting continents, the relentless dance of tectonic plates across the globe. They also accounted for the formation of new oceans through seafloor spreading, the creation of vast ocean basins, and crucially they incorporated the slow, powerful churn of the Earth's mantle, the engine-driving plate tectonics. The simulations that best matched the characteristics of today's gravity hole, that peculiar dip in the Earth's gravitational field, all pointed to a single, compelling culprit: a vanished ocean, a body of water lost to the mists of time. That ocean was the Tethys, a vast prehistoric seaway. About 120 million years ago, during the Cretaceous period, a massive slab of the Tethys seafloor, a dense section of oceanic crust, began its slow, inexorable descent, sinking deep into the Earth's mantle at a subduction zone. This process was driven by the relentless northward movement of the Indian Plate. This cold, dense slab plunged ever deeper, a vast sheet of rock sinking into the Earth's hot interior. As it descended, it displaced hotter, lighter rock within the mantle. This displacement created a significant disturbance, disrupting the delicate balance of the mantle's structure and dynamics. The effect was akin to a stone dropped in a bowl of soup, triggering powerful convection currents within the mantle, immense flows of molten rock. These currents, in turn, set the stage for the formation of the gravity dent, the anomaly that had puzzled scientists for so long. The ghost of this lost ocean, the Tethys, would soon exert its influence, reshaping the very structure of the Indian Ocean from deep below the surface. But the story of the Indian Ocean's gravity hole and the Tethys Ocean's legacy was only just beginning. The story of the Tethys Ocean doesn't end with its disappearance from the surface. Its legacy continues to resonate deep within our planet. The sinking Tethys slab didn't vanish, it embarked on a journey to the Earth's lower mantle. Over eons it settled at the mantle's base, a graveyard of ancient seafloor. This immense slab didn't just lie dormant, it acted as a catalyst, disturbing massive blobs of hot, buoyant rock that have resided there for potentially billions of years. These blobs are unlike the surrounding mantle material. These ancient mantle structures, vast and enigmatic, especially the one beneath Africa, were subtly nudged and influenced by the slab's arrival. The immense weight and pressure of the Tethys slab subtly altered the dynamics of these deep-seated features. In response to this disturbance, plumes of hot, low-density rock began to rise from the core mantle boundary. These plumes are columns of superheated material, ascending slowly but surely through the mantle. The process is similar to bubbles forming and rising in a pot of boiling water, driven by differences in temperature and density. These plumes, predicted by sophisticated computer simulations that model the Earth's interior, spread laterally beneath the Indian Ocean, creating a vast, buoyant column of lighter material that influences the region's geology. This column is less dense than the surrounding mantle. This vast accumulation of lighter material is the direct cause of the gravity low, a subtle but measurable dip in the Earth's gravitational field. It signifies the presence of less dense rock nestled beneath the ocean floor, a stark contrast to the denser material that typically resides there. The gravity dent, as it's sometimes called, is not a void or an empty space. It's a crucial sign, a telltale indicator of something lighter and less dense residing deep within the Earth's mantle. It's a delicate balance of forces at play, an echo of a lost ocean reverberating through the Earth, and a stirring of ancient mantle plumes responding to these changes. The simulations, based on extensive data, have linked events separated by millions of years and spanning thousands of kilometers, revealing the intricate connections within our planet. Science needed proof beyond simulations. Seismic tomography, using earthquake waves, revealed mushroom-shaped plumes of hot, buoyant rock rising beneath the Indian Ocean, just as predicted. These low-velocity zones are the fingerprints of mantle plumes. Volcanic hotspots like Reunion and the Comoros Islands are surface evidence of this deep upwelling. The chemistry of their lava points to a deep mantle origin. Multiple lines of evidence, computer models, seismic imaging, and volcanic rocks, confirm the plumes are real. The Indian Ocean Geoid Low is a living record of Earth's deep, dynamic processes. It's a planetary mystery solved by connecting the surface to the depths. Optical illusions can trick our minds, creating perceptions that don't quite align with reality. They play with our senses, exploiting the way our brains process visual information. But unlike those fleeting tricks of the eye, the Indian Ocean's gravity hole is a real measurable anomaly, a dip in the Earth's gravitational field that scientists have been studying for decades. It's not a figment of our imagination but a tangible feature of our planet. This gravitational anomaly provides a unique window into Earth's restless interior, offering clues about the processes churning deep beneath the surface. It allows us to peer into the hidden engine that drives our planet. The mantle plumes, those upwellings of hot rock from the Earth's core, beneath the ocean are still rising, pushing and deforming the crust above. These plumes are like giant conveyor belts, transporting heat and material from the depths of the Earth. This constant upward pressure is actively shaping the crust above, influencing the landscape of the ocean floor and contributing to the movement of tectonic plates. The geoid low, this unusual gravitational dip, formed only about 20 million years ago, a relatively recent development in Earth's long history. In the grand scheme of geological time, 20 million years is merely a blink, a fleeting moment in the planet's multi-billion-year existence. And the Indian Ocean Geoid Low isn't a static feature. It's still evolving, changing shape and intensity as the Earth's interior continues its slow, relentless dance. The sinking of old, dense ocean crust back into the mantle, a process known as subduction, and the compensating rise of new mantle material to the surface, creating fresh oceanic crust, are the key processes that drive the planet's continuous renewal, constantly reshaping its surface and redistributing its mass. The Indian Ocean Geoid Low is a snapshot of this ongoing cycle, a visible manifestation of the Earth's internal engine at work. It's a powerful reminder that the same forces that are responsible for building continents, raising mountains and shaping the oceans are still at work, constantly modifying our planet on a timescale that dwarfs human experience. These forces operate silently, invisibly, beneath our feet, shaping the world we inhabit in ways we are only beginning to understand. The future of this anomaly is uncertain. Geological processes are notoriously difficult to predict with precision. Will new volcanic islands rise from the depths of the ocean, adding new land to the map? Or will gravity eventually reclaim its hold, smoothing out the dent and returning the region to a more uniform gravitational field? For now, the Indian Ocean's gravity dent remains a beautiful and enigmatic mystery, a puzzle that continues to challenge and intrigue scientists. It serves as a potent proof that our world is far more dynamic, more active and more alive than it might initially seem from our limited human perspective.